Now in chapter 5, you are going to learn about design of machine element subjected to direct and bending stresses, right? Now what does title says? If you look at the figure very carefully, here there is a frame which is bolted with the 4 bolts on a vertical column, right? Now this frame is subjected to force F. Now you know this force screw is having a center. From the center the force is applied at a distance. So this is going to twist, right? But because it is bolted, the frame is trying to bend over here, right? It is trying to bend over here, okay? Now in this chapter, because of this, there is a direct stress are also acting on all these 4 bolts, right? Along with that, because the load is applied at a distance, it is going to create a bending. So we are going to study those machine element in which we do have a direct stress applied always, and also along with that we also observe the bending stress. So how can we find the dimension of such element? So that we are going to learn in this chapter. Before that, we need to understand what is eccentric loading. If you recall this figure, this is the figure of eccentric loading. What is eccentric loading? Now loading means to apply force, right? Or you can say simply load on an element. But it is, a word is given eccentric. An external load whose line of action is parallel but does not coincide with centroidal axis of machine component is known as eccentric loading. Let's try to understand by taking the example of round bar, okay? This is round bar and this is center axis, right? Now I am applying a tensile load exactly on the center axis, right? So I have applied a load P exactly on the centroid axis. So this is not eccentric loading, it is centric loading or direct stress, okay? But same load, if it is applied by at a certain distance from the centroid axis, that means the action of load or line of action of load is offsetting by certain distance from this geometrical central axis. In that case, same load is referred as eccentric load. Now because of this, the stresses developed in component is of 2 types. One is direct and second is bending stress. So the distance between the central axis and machine component and the eccentric loading is called eccentricity. So this offset distance that you see in this figure, this distance is called E. It is denoted by E, right? It is called eccentricity. It's a simply offset distance of line of action of load from the central axis. अब इससे क्या होगा? Simple आप imagine करें. If the load is applied exactly on the center, let's say it is compressive load. Let me draw in 3 dimensions so you can understand, right? Like this. So this is center. Now I am exactly applying load in the center. So that will be the case of purely a compressive load. But the same load, if it is offsetted by certain distance from the centroid axis, let's say over here, which is shown in this figure. Because of that, if this is the case, same part is going to bend in this manner. Same part is also subjected to compressive stresses. Along with that, it is going to bend in this manner, right? Because we are having eccentric loading. So this is what the concept of eccentric loading. So when you apply such load, it is also going to experience direct stresses as well as bending stresses. We know how the nature of bending stresses, right? So in the side of bending side, you experience compressive stresses, and another is you are going to experience tensile stresses of a same magnitude, but in opposite direction. So this is the figure which describe the bending stress, right? So this part, let's say compressive, and this part, let's say the tensile, and exactly at the neutral there is no stress, okay? So when such component which is subjected to eccentric loading, we have to combine both the stresses together, right? That is direct stress and bending stress. So when you combine this, we are going to get regional stresses like this, where the maximum stress is on one side it is higher, on another side is very lower, right? So but just by looking at the figure, we can say we have to consider this maximum stress, right? Let's say load is applied on a right side. So this right part is subjected to a very high value of stresses. So we have to find out this maximum value of stress, right? This is minimum. It is of no use, but it is of compressive nature, or this is of tensile nature, right? So we need to combine the stresses together to find out the dimension of such component. Now, which are the components subjected to eccentric loading? So first, just look at it, the clamp, right? This is clamp that we use in carpentry. Even we also use in the welding side, welding workshop, to grip the plate together. So when you wound it, tighten up by putting a plate over here, so it apply load over here, right? So because of that, this frame is tried to bend like this, okay? So here, this is the bending possibility, right? So here it is going to bend along with the vertical load. So this is a classic example of eccentric loading. Similarly, you can have a bracket machine base, right? Let's say this is a radial drilling machine, where the drilling arm can be swing around like this, and the drilling head can move in and outer. So as it moves away, maximum distance is observed, right? So this is E. So because of that, this radial arm is going to bend, and that also going to bend this vertical solid pillar, right? So this is the classic case of eccentric loading. So here the design of these dimensions, that is this pillar, right, diameter D, that we have to consider by applying load, thrust load, as well as the bending load. Similarly, you can consider the riveted and bolted structure, right? So this is a welded structure and this is bolted structure. They are also going to subject a eccentric loading. So all of these components are basically subjected to eccentric loading. Now let's see how to design it. Now, stresses due to eccentric loading. It's the same figure that we studied earlier. Here, direct compress and tensile stresses on cross section is, that is direct stress I am talking about, which is very simple. Load applied divided by the cross section. So here it is rectangle cross section, right? It is rectangle. It is B into H. Very simple. If it is circular, it's going to be pi by 4 D square. Okay. As in eccentric loading design, the component is subjected to direct stresses as well as bending stresses. Now, bending stresses are introduced due to the eccentricity, right? So for that, we know the equation is bending stress is equal to bending moment divided by section modulus Z. Here, bending moment is simply summation of load into its distance. So the bending stress is calculated by bending moment divided by section modulus Z, that is P into D divided by Z. Okay. So now let's consider the figure. So because of eccentric loading, we have to combine direct stress plus bending stress. Now because of the combinations, first need to understand in which direction load is applied, whether it is tensile or whether it is compressive. So let's consider the section. Let's say this is point 2 and point 1. So we are considering what will be the maximum stress at section 1. That means at this location, if I draw in 3 dimensions because of eccentric loading, and what would be the stresses at the section 2, right? So if you look at the figure, when you combine the direct stress and bending stress, you'll find the resultant stress pattern is like this. Now same if you carry forward, you can say at section 1, there is a maximum stress because of addition of direct stress and the bending stress. But the similar is observed in a reverse manner, where at section 2, the direct stress and the bending stress are opposite in nature, and that's why we have a smaller resultant stress, right, which is in negative direction or opposite direction. So we can say it is of compressive nature, right? Both the stresses are having different value as well as both are having different directions. So we can term one as a tensile stress and second as a compressive stress. This depends where do you apply the eccentric load. Let's say if you applied on this side, so section 2 will have a maximum stress and the section 1 will have a minimum stress, right? So again, look at this figure, okay? So here we are applying, this is a square section, we are applying the load P along the x-axis at E distance, and this is direct compressive stress, this is bending stress, where the right side portion will be subjected to compressive nature because of bending of in this pattern, bending of in this direction. So the bottom part is compressive stress and the opposite side is tensile stress. When you combine these together, what will happen? This part gets subtracted, so hence the overall resultant part will be smaller. But these both are compressive nature, they get added and they make it larger triangle like this one. Okay, so here this is the biggest value of stresses. We have to ignore the small value. We have to design the dimension. We have to find the dimension based on this maximum value. This maximum value can be of compressive nature, can be of tensile nature. Depends how you apply the eccentric load, whether it is inward or outward. Okay. Now let's try to consider the equations. Now total stresses on each cross section, right? Let me draw over here so you can understand very well. Okay. So here, this is x-axis and this is y-axis. The load is applied over here. The load is applied at P point at a distance E. So this is section 1 and this is section 2. So the total stress will be either you can add the direct stress or you can subtract it. Over here, if it is compressive load, there will be addition. Over here, if it is the load applied is compressive, and at this section it will be the subtraction. So here this is direct stress plus minus bending stress. Now if you look at the section 1, the total stress at section 1 will be the summation of direct stress plus bending stress. Similarly at section 2, it is direct stress minus, because the as bending stress is in downward direction and the direct stress in upward direction, or you can say the reverse, depend upon how you applied the load, whether it is compressive or the tensile one, right? So here because of that we have to subtract the bending stress, right? This is going to be of lower value. Addition is always going to give you the higher value. So for designing purpose, we have to choose higher value of stress. Higher value of stress. It can occur at section 1 or it can occur at section 2 depending upon how the eccentric load is applied and what kind of nature, whether it is tensile or compressive. Now let's take a numerical and try to understand it. Okay. Now here problem number 1. A 20 kilonewton vertical load is acting of the end of C clamp. So let me draw a C clamp like this. Okay, whose cross section is rectangle. Whose cross section is rectangle. Okay, so let me draw over here. This is rectangle section. Okay, H and B. Here the relation is given. H is 2 times B. Having rectangle cross section. Now perpendicular distance between the load axis. We are applying load over here, P, and the geometrical axis. So distance between the line of action of load and the geometrical axis is eccentricity, or you can say the neutral axis of the section, is 140 millimeter. So E is given 140 millimeter. Now find the dimension of cross section. So what is H value? What is B value? For the clamp, and permissible stress is 100 Newton per millimeter square. That means at section 1, at sections 2, you have to find the stresses. It should not more than the 100, right? So we can take given value of permissible stress and find the dimensions. Okay, so let's proceed and try to understand the theory. Okay, now here we are going to call this one as a section 1 and section 2. Okay, now direct stress sigma D is equal to P upon A, and the bending stress is equal to M bending moment divided by section modulus Z. So bending moment is simply P into E divided by Z. Now what is Z? Z value is very simple, 1 by 6 BH square. Here I can take H is equal to 2 times B. So 1 by 6 B into 2B square. So it's going to be 4 by 6 and B cube. So ultimately it is 2 by 3 B cube, right? Now let's find the direct stress. Okay. So here at section 1, I'm going at section 1. Here load is applied is vertical. Try to understand, the vertical load is applied. So the bending will happen in this manner. Okay. So the tensile nature and bending stress will get added at section 1. Very simple, right? So direct stress plus bending stress. So here direct stress is given by P by A. What is the value? 20 kilonewton. we don't know the section, that is H into B, okay, plus bending stress, that is given by P into E divided by Z. So load is 20,000, eccentricity is given 140, and this value is 2 by 3 B cube, right? That is Z value. That is Z value. I am simply adding bending stress and direct stress for section 1. Okay. So let's simplify it. Okay. Now how to simplify it is very simple. We can take this H is equal to 2 times B. So it becomes the 2B square. So I can write whole 2B square. Okay. Now here you have to apply certain mathematical formula, right? Now similarly at section 2, it is very simple. It's going to be a direct stress minus bending stress. So definitely this value is going to be a lower value, right? And this value is going to be a maximum value. This is going to be a maximum value. So we are going to consider stress at section 1 for designing purpose. Okay. So resultant stress at section 1 will be maximum. So that we are going to take as a reference, right? So what we can do here is, let's continue this equation, right? So maximum stress is occurring at section 1, which is, let's say I'm going to cancel out these two, right? So that's going to be 10,000. Okay. So that is B square plus, now let's take it, this is cancel out and goes up, right? So that way I'm going to find it. The value is 42 10 raised to 5 divided by B cube, right? Now this maximum value is given 100. Okay. That given is 100 value. So again, I'm going to take 100,000 B square 42 10 raised to 5 B cube. Okay. Now let's simplify. Let's multiply B cube on the both side. So multiplying both side by B cube, right? So this become, or simply let's cancel out. Before that, let's cancel by 100. Okay. So this 2 has gone and this become 3. Okay. So here it will be B cube. This is going to be 100B because of cancellation of B cube and into B, plus this is going to be 40,000. Okay. Now let's simplify it. B cube minus 100B minus 42,000 is equal to 0. Now we have to solve these equations, right? Now how can you solve this? So let's take simple thinking. Here B cube minus 100B minus 42,000 is equal to 0. Now using trial and error method, what we can do, we can simply assume a diameter, right? Let's assume a diameter B, diameter not, but the dimension B is equal to 40. If you take 40 and replace in this left side, you are going to get value. Left hand side is equal to, let's say it is 1800, right? Which is positive side. So we have to reduce the value. So let's take little lower value, let's say 34, and put it over in the same equation and find out what is left hand side. Now it comes out to be minus 6096. So what it says, on a timeline, we want 0 for a value of a B. ऐसा value find करना है B का, तो that equation gives the 0. So for B is equal to 40, जब हमने 40 लिया, तो over left hand side comes out to be 18,000, which is positive value. But when you take it B is equal to 34, we are having minus negative values 6096. What it says, our answer lies between the average of 34 and 40. तो इन दोनों के बीच वाला जो भी B का वैल्यू है, that going to give the lowest or nearest value to the 0. Okay. So let's try the average of these two. That is B is equal to 36. So for B is equal to 36, we have a value of left hand side is equal to 1056. Okay. So this is the closest value. If you take, let's say 35, you may think this is the positive and this is negative, right? So average of that may give you the nearer value to the 0, right? But here taking a 35 is also coming out a negative value, which is more than the 105. So from above observation, we conclude that the value B is 36, which is very closer to the 0, right? So that is 156, right? So B value is 36. Okay, this is called trial and error method. You have to assume certain value. If you are come up with the left side positive, then reduce it. If you are having your assumed value going to give the negative value, then increase it. Somewhere you will find a positive and negative value. That means your answer lies between the border of these two value, where the left hand side is, once it is positive, second time it is negative. So in between there is a middle you can say value. Okay, now here B is 36. Now what is H value? It is 2 times B. Okay, so 36 into 2, 72 millimeter. So the rectangle section of C clamp H is equal to 72 and the width is equal to 36 millimeter. Okay, so this is the dimensions we have to keep to take eccentric load of 20 kilonewton at an eccentric value of 140. So this is what the how to design the section subjected to eccentric loading. Now let's take another problem to understand further. Okay, a hollow column of drilling machine has outer diameter 124. So it's a hollow column, right? And it's a drilling machines. So drill is fit over here, and we are applying the drill load. Okay, so the outside diameter is 124. And the inside diameter is how much it is? 84, right? That is this diameter and this diameter. Okay, so it's a hollow column. Now distance between the column axis and the load applied is 300 millimeters. So this is eccentricity. So dimension is given, eccentricity is 300 millimeter. Okay, it is 300 millimeter. So this distance is 300 millimeter. Now outer diameter is 124 millimeter. Inside diameter is 84 millimeter. Now calculate the maximum stresses induced in the cross section. So here we have to find out what is the value of maximum stress. It can happen either at section 1 or section 2. So let me call it 1 and 2. Okay, so I'm redrawing the whole section over here. So because of load, there are going to be stresses at the section 1 and section 2. We are applying the load vertically, so definitely it is going to bend in this manner. So at section 1, it is going to give you the maximum value, that is a summation of direct stress and the bending stress. So we are going to directly find the induced stress at this section as well as in these sections. Okay, now here the direct stress is equal to P by A. Here load is given 3400 Newton. Okay, now because it is hollow section, I can write like this: pi by 4 d square. The outside diameter is 124 raised to square minus inside diameter. So I have to take the annular area. That is, this is the ring area on which the direct load P is acting. Okay. Now direct stress comes out very simple. It comes out 0.52 Newton per millimeter square. So this is the direct stress value. Okay. Now let's find the indirect stress or bending stress. Bending stress is equal to P into E divided by section modulus G. Here load is given 3400. The eccentricity is 300 divided by Z. Okay. Now because this is the hollow circular section, Z value will be pi by 32 d raised to 4 divided by do. This is the value, right? So we can calculate it. We can calculate it separately by putting the value pi by 32. The outside value is 124 is to 4th power. Inside is 84 is to 4th power divided by 124. Z. Now Z value is going to be 148 10 raised to 3 10 raised to 3 meter cube. Let's find the bending stress. Now here that Z value is 148. So 148 10 raised to cube. So that bending stress comes out to be 6.892 Newton per millimeter square. Okay. Now considering the section, let's find the stresses. Okay. So at 1 and 2. At 1 it is going to give you the summation, that is direct stress plus the bending stress. The direct stress plus bending stress. So now direct stress value is 0.52 plus the 6.892. Now the value is 7.412. Now this is of tensile nature. Right? At section 2, the stresses at section 2 will be the direct stress minus bending stress. इस तरह से वो compress होने वाला है, right? So direct stress is upward, but bending stress is opposite. So we have to subtract the bending stress from the direct stress. So here it is 0.52 minus 6.892. This is going to give you minus 6.372 minus 6.3. So this is compressive in nature, right? Compressive in nature. Okay. The value is again Newton per millimeter square. I hope it is clear to you. Now let's solve the problem number 3. A spindle of drilling machine is subjected to maximum load of 10 kilonewton during operations, right? So it is solid cast iron column. Okay, it fixed on a base. We do have a drill arm and drill spindle is fixed over here, and we are applying the vertical load, right? So this is eccentricity. So here in this numerical we have to find out the diameter of this solid column. So determine the diameter of solid cast iron column if the tensile stress is limited to 42 megapascal. If we consider the load, vertical load, let's say here it is, the direction is not given, but let's assume it is vertical, right? So definitely at section 1 it is going to be maximum, and at section 2 it is going to be minimum. So here the distance between the axis of spindle and the axis of column is 400. So eccentricity is 400 millimeter. All we have to do is find out the diameter of this solid column. It's a very simple numerical. Now by considering or assuming the load is applied vertically, hence the vertical tensile direct stress is upward, as well as the bending stress at section 2 is also upward. So this will be the case, right? This will be the case. So here it going to give you the maximum stress. Okay, maximum stress at section 1. So let's find directly at section 1. So maximum stress at section 1 is simply summation of direct stress, that is P by A, and the bending stress, in which we have bending moment P into E and section modulus Z. Okay. Now let's say the maximum safe stress is given 42. Okay. The load is given, how much it is? 10,000 Newton. Now it is solid diameter. We have to find as pi by 4 d square plus again 10,000 load into eccentricity is 400 Newton divided by Z. Z is simply because it is circular, so pi by 32 d raised to cube. Okay. So here we can replace that value pi by 32 d raised to cube. Now student, you have to learn the skill of simplifying these equations. So here what we are going to do, we are going to divide this 10,000 by pi by 4 as well as 4, or you simply take the 4 upper side. So simplify this term. Okay. Also you have to simplify this term. So I'm going to write is 42 1 2 739 divided by d square plus 40764 divided by d cube. Okay, so I have divided this value by pi by 32. Similarly, I have divided 10,000 by pi by 4. So I'm getting this simplification. I have ignored the decimal point, which were very of a low value. Okay. Now again, I'm going to divide by 42 on both sides. So dividing both sides by 42 and multiplying by d cube. So what we have here is very simple, d cube. So सबसे पहले हम 42 से divide करेंगे तो this become 1. Then we are going to multiply by d cube. So this is d cube. Here again, this part also subjected to division by 42 value. So total comes out to be 3.3 into d because of multiplication of d cube. Plus what we have is division, dividing this value by 42 and also multiply by d cube. So d cube will cancel out, right? So it is 970 and 579. Now let's take its simplification. D cube minus 303 d minus 970 579 is equal to 0. Now you have to solve these equations, right, by taking trial and error methods. Okay, so let's try over here. Very simple. So by considering trial and error method, let's assume first value. Let's assume the diameter is 80. Okay, now put this value in this equation. So find out left hand side. So left hand side is comes out to be minus 482 819. Okay, so on a timeline I want a 0, and for 0 I want to find out the d value, right? So as assumed d is equal to 80, I am getting very lower negative value, 482,819. So I have to increase. So I have to increase 80. So I'm going to assume d is equal to 120, right? So let's increase the value by 40. So it is, so left hand side is going to be again 721061. Now it is positive, this is negative, hence the positive value is 721061. Now meaning of this, if you take average of this, so our answer lies between 80 and 120, which is going to give you the nearer value to the 0. So what is average? 100. Let's say d is equal to 100 and find out the left hand side. So for 100, it's going to be minus 879. This is the closest value, right? This is the closest value possible by 100. If you take d is equal to 102, it will be on positive side, positive by more than 800 value. So considering above readings, we conclude that diameter d is equal to 100 millimeter, right? So we have to keep the solid diameter of this column is equal to d is equal to 100 millimeter, right? This is how you can solve the numerical on eccentric loading. Okay.